talk is the formal verification of a distributed dynamic reconfiguration protocol. This is work conducted at Northeastern University. I believe William Schultz is the speaker.
That's correct. Yeah, he's just setting up his laptop.
Okay. We'll just wait a moment while William gets everything set up. Okay, I can see the slides now. Okay. So, okay, William, you can take it away.
Okay. So hello, my name is Will Schultz. I'm a PhD student at Northeastern University, and where I'm advised by Professor Stavros Tripakis, and I'm going to present today about our work on formal verification of a distributed dynamic reconfiguration protocol. And this work was completed jointly by Ian Dardik, a master's student there, and myself. He completed a large amount of the work on doing the TLA plus safety proofs for this. So I'll start by motivating why we might want to do these kinds of formal verification efforts for protocols like this. So generally, distributed consensus protocols like Paxos and Raft now serve as the foundation underlying many modern fault-tolerant data storage, database, replication systems. And to be resilient to failures, these systems must have an ability to do what we refer to as dynamic reconfiguration, that over time, if we want the set of servers operating a consensus protocol to change dynamically, if you want to add or remove nodes to perform a software upgrade or just to elastically scale your cluster, you need to be able to do this dynamic reconfiguration process. But typically, designing these types of dynamic reconfiguration protocols has been somewhat challenging. And in past, they've been subtle and difficult to get right, as exemplified in one particular case by a safety bug, for example, that was discovered in one of Raft's proposed simpler single server change reconfiguration protocols that was only found after its initial publication. So this is one case that makes these, one example that illustrates that these are good types of protocols as a target for formal specification and verification efforts. So for example, Raft was, in its initial publication, did have a formal specification, and then there was a later verification effort, but this did not include or cover the reconfiguration aspects of the protocol. So MongoDB is then a distributed database with a replication system that uses a consensus protocol derived from Raft. So it's conceptually very similar with some extensions and optimizations and modifications, but the underlying protocol is very similar. And it employs a recently published protocol that we call MongoRaftReconfig for doing dynamic reconfiguration. And this protocol, MongoRaftReconfig, was presented and formally specified in prior work to this. And that work also included a so-called manual safety proof, like a pen and paper proof, but not a formalized safety proof. So the goal of this work was to develop a formal safety proof using the TLA plus proof system to establish the safety properties of this reconfiguration protocol. So just to summarize, basically the contributions of our work were first we're presenting a formally stated inductive invariant for the MongoRaftReconfig protocol in the TLA plus specification language, and then coupled with this, a machine-checked TLA plus safety proof of both this inductive invariant and then the high-level safety properties of the MongoRaftReconfig protocol. And so to our knowledge, this constitutes the first formally verified safety proof of a Raft-based reconfiguration protocol. So now I'll just give a little bit of brief background on this protocol and its formal specification, which existed in prior work and we built on top of. So as I said, MongoRaftReconfig is a dynamic reconfiguration protocol that's used in the MongoDB replication system, and it was formally specified in TLAPS, which you may be familiar with, is this, right, a high-level specification language that's typically used for specifying concurrent and distributed protocols at a relatively high abstraction level. And the existing specification was around 400 lines of TLAPS at a high level of abstraction. So just to illustrate briefly at a very, very high level what this type of specification looks like, in TLAPS you just simply define your system as a state machine, as a transition system given by an initial state predicate that defines the set of allowed initial states of your system, or your distributed system as viewed as a global object essentially. And then you define your transition relation also as a logical predicate over pairs of system states that defines the set of allowed system transitions. And then your overall system specification is just a single temporal logic formula, which is the conjunction of these two subformulas. And again, without going into really any details of the protocol itself for sake of time, this is one example of one of the protocol actions. So basically one of the possible transitions that the protocol can take, for example, executing a reconfiguration on a certain server of the system. Just to show you how it would be defined in TLAPS as one example. Okay, so now I'll talk about our inductive invariant, which constituted a fairly large portion of our verification effort in terms of establishing safety of the protocol. So just to give a very brief theoretical background again, the basic induction rule is that if you have a protocol defined by its initial state and next state predicate that satisfies some invariant, which we call safe, typically we need to find an inductive invariant satisfying the basic conditions that the initial states satisfy the inductive invariant and that the inductive invariant is closed under the transition relation, and that the inductive invariant is of course sufficient to prove your safety property, your invariant, and typically the inductive invariant will be a strengthening of your given invariant. So our inductive invariant for MongoRaftReconfig consists of 20 total logical conjuncts, and this inductive invariant was developed over the course of approximately 1 to 2 human months of work. And so just to give you a very high-level picture of what this thing looks like, again, without being able to describe all the details, as I said, it's a collection of 20 sort of sub-invariants that establish properties about the protocol. It can be understood to some extent in subcomponents. So at the top, there's a type correctness predicate, which establishes a simple type correctness property of the state variables of the system, which is needed because TLAPS is fundamentally an untyped formalism. So you need to establish that up front. And then there's a group of invariants that say certain things about elections. In Raft-based protocols, for example, there's a certain property that says there's basically needs to be a unique leader per each round of the protocol. And this is somewhat non-trivial to establish in the case of dynamic reconfiguration. There's a group of log invariants which establish properties about log entries on different servers of the system, consistency properties about them. And then there's an additional group of invariants that deal with how log entries are committed on leaders and propagate to new leaders from old ones. And again, just to give a very surface level example of what these things look like, we dive into one of these conjuncts as an example to see its definition. Typically, each individual conjunct is comprised of several, contains both universal and existential quantifiers, typically over the parameters and state variables of the system. So just to provide one example of the many conjuncts of this invariant. So the process of discovering an inductive invariant for a protocol of this complexity is a highly non-trivial task, but it can help, especially when trying to write down a formally stated inductive invariant, to have a method for debugging the invariant. So if your invariant is not actually correct, if it's not inductive, checking whether that's the case. And we employed a probabilistic checking approach that was proposed a couple years ago by Leslie Lamport that just makes use of the TLC model checker, which is an explicit state model checker for TLA+ specifications. And it's able to find counterexamples to induction. So basically it just looks for state transitions S to S prime, where S satisfies your inductive invariant and S prime violates it, giving you a concrete instance telling you why your invariant is not in fact inductive. And this works on, due to the fact that TLC is an explicit state model checker, it works on finite protocol instances. So you have to bound your state space essentially to be finite, but for example, limiting your system to have a finite number of nodes or servers. But we found it to be quite useful in developing an inductive invariant and finding bugs, and then developing an invariant that we later proved formally in the proof system. So with that, I'll now talk about our TLA+ safety proofs, which consisted of proving our inductive invariant and then using that to establish the high-level safety properties of the algorithm. So a little bit of background here again, the TLA+ proof system, which is referred to here as TLAPS, allows for the writing of machine-verified proofs in TLA+. And proofs are written in a particular hierarchical style, so where you have what are called leaf proof steps that can be validated automatically by some kind of backend solver, like an SMT solver or Isabelle, and there's a variety of backend solvers the tool can use. So there's some amount of human guidance in terms of developing the structure of the proof, and then smaller steps of the proof are to some extent automatically discharged to a backend. So these hierarchical proofs structurally consist of a series of statements or logical assertions, the conjunction of which should imply an overall top-level goal. And each statement of a proof can then be either what's called a leaf proof or consist of a further proof, which is another sequence of proof statements. So as a very basic example, if you're trying to establish a logical assertion P, which is stated here by saying theorem P, it might be the case that statement 1, 1, 1, 2, and 1, 3 taken together are sufficient to logically imply P. And that's basically stated in this proof by this QED expression at the bottom that says the overall top-level goal is implied by steps 1, 1, 1, 2, and 1, 3. And then steps 1, 2, and 1, 3 may, for example, be trivial, or they may be self-evident and don't require further proof. But statement 1, 1, for example, may be non-trivial, and it may require itself an additional proof. So you can just apply this hierarchical structure recursively, providing another proof for that statement itself. So our TLAPS safety proofs for the protocol, they establish our inductive invariant, and then they establish two key high-level safety properties of MongoRaftReconfig, which are referred to as the LeaderCompleteness property and the StateMachineSafety property, which are safety properties that also appear in the Raft protocol. Again, without worrying about the details of the protocol, you can at least see how these properties, which are invariants, so they're predicates over states of the system, would be stated in TLA+ as predicates. LeaderCompleteness essentially says something about the fact that log entries committed in a certain round of the protocol must be persisted to later rounds, to primaries in later rounds. And this state machine safety property says something to the effect of if two log entries appear at a particular log index, then they must be, in fact, the same log entry. And again, just to provide a very high-level example of what these proofs look like without being able to explain all the details, this is an excerpt of one of our TLAPS proofs for establishing this high-level state machine safety property. Of course, it relies on many auxiliary lemmas and things. So the top-level statement of the theorem or the lemma here says that our inductive invariant should imply this property, state machine safety. And again, skipping over many details, as an example of a structure of a proof, this ends up breaking down into a kind of case analysis where we reason about a certain value of these two objects, C1 and C2, where we say we look at the terms of these objects and reason through the cases. So the case where C1's term is not equal to C2's, and then additional cases where the term of the first is greater than the second, and the term of the first is less than the second. And then the overall proof concludes with a step that basically says by these steps above, 1, 4, 1, 9, and 1, 10, this should be sufficient to have established, to imply the top-level goal of the theorem statement. So in terms of some statistics and details of the proof effort, its development took around 3 to 4 human months of work, and this is not including the development of the time to develop the inductive invariant. And some statistics, in total, it's around 3,200 lines of TLA+, of which there are around 360 lines just for defining the protocol specification itself, and then 140 lines of which are just for defining the inductive invariant itself. And in total, we ended up with 70 formally stated lemmas. The decomposition of which is somewhat up to the user, but this was the ultimate structure of our proof. So we had 78 lemmas, then 3 top-level theorems which established the overall safety properties and rely on these lemmas. And one other potentially interesting statistic is once we have the proofs written, to go through and verify the proofs, to check the proofs from scratch is not so fast. It roughly takes around 40 minutes to check all of the proofs on like a modern MacBook. This is more or less consists of calls to an SMT solver or another backend in terms of what computation time is spent on. So with that, I'll just wrap up with some conclusions and then some possible future work and takeaways I'll mention. So in summary, in this work we present our formally stated TLA+ inductive invariant for the MongoRaftReconfig protocol, and then also the formally verified safety proofs in TLAPS of MongoRaftReconfig, which consists of a proof for our inductive invariant and the high-level safety properties. And as I mentioned, to our knowledge, this constitutes the first formally verified safety proof for a Raft-based reconfiguration protocol. So then some lessons and takeaways and possible future work. So generally, manual development of formal inductive invariants for protocols of this complexity is non-trivial and time-consuming. So we would be interested in seeing to what extent that process can be automated. In recent years, there are tools like Ivy and things that have tried to push in this direction. And in even the last couple of years, there have been tools that tried to see to what extent inductive invariants for a certain class of distributed protocols can be discovered fully automatically. So those tools were not developed for TLA+, but it'd be interesting to see what ideas can be applied there. And yes, formal proofs in TLAPS are laborious, even with strong prior intuitions on correctness of the protocol. And I think as it has been observed generally, that they also can be brittle to changes. Even changing the statement of a definition or a lemma, maybe even just in an aesthetic way, may cause you to have to update your proof. We did find, though, that hierarchical proofs in TLAPS can be a nice way to modularize proofs and break them down into small, manageable steps. But there are a variety of tooling things that could be improved, generally just in the user interface of TLAPS, and perhaps better counterexample generation facilities that if, for example, you're trying to prove a step, a certain verification goal that is not in fact true, getting a concrete counterexample would be helpful in certain cases. So if you want to take a look, you can see all the proof artifacts in the protocol specification at this link. So with that, I'll wrap up and take any questions.
Questions here locally in Philly?
Yes, do we have any questions in Philly?
Yes, just a second.
Hi, thanks for the great talk. I had a little question about the complexity of the invariant. So you had like 20 clauses, and I was wondering, like, do they actually depend on each other in the induction proof, or can they be broken into individual inductive invariants?
Yes, I guess in the way that we did the proof, there's a natural decomposition of basically proving, breaking the induction step down by each protocol action and then by each conjunct of the invariant. So at least in that sense, which is a very naive decomposition, which is what we did, it breaks your it breaks this very large problem down to smaller ones, and you have many small problems, but you have to just prove them individually. Yeah. There may be like more elaborate decomposition ways we could have decomposed the invariant, but we sort of took a relatively naive approach in that sense. Yeah.
Yes. Any other questions?
Yeah, we have one more question here.
Okay.
Yeah, thank you for the talk. So you mentioned that you spent about 1 to 2 months developing the invariant and another sort of 3 to 4 months doing the proof. I'm wondering to what extent those two phases were kind of intertwined, because I would expect you to figure out the invariant while trying to do the proof, or did you stage it somehow?
Yeah, that's a good question. It was fun. I mean, the way it turned out in this particular instance was that we actually had 2 people, and not even planned this way, but it just worked out that way, that basically myself working more on the inductive invariant and another person working more on the proofs. I don't know if that was the most efficient breakdown of work, in the sense that the intuitions you gain from the inductive invariant probably do help in the proof, and vice versa. But to some extent, I do feel like the inductive invariant, at least intuitively, can sort of be decoupled. The development of that in terms of how you think about a protocol and its correctness can sort of be decoupled from actually proving the inductive invariant. But I could be wrong about that, but that was my feeling about it, maybe. Yeah.
And one more question here from Philly, if that's okay with you, Owen.
Yes, yeah, that's great. We don't have any online, so.
Hi, thank you for the talk. I just wanted to ask if you can speak about any patterns or overlaps between your TLA plus verification efforts and the verification efforts for multi-paxos that were also done in TLA plus?
Sorry, what was it? What was it?
The TLA plus verification efforts that were also done for multi-paxos. So, like, is there any overlap in your work, or did you like have any patterns that you recognized, or I mean?
I guess I don't know. I mean, I'm aware of like this. There's somebody, Chand, and maybe in 2016. I'm not sure the work that you're referring to about the multi-paxos.
I'm not terribly familiar with it either. I just know that there has been a TLA plus verification effort for multi-paxos, and was wondering if you were aware of that and could speak about it at all.
Okay. Yeah. I guess so. There's one like notable effort of verifying multi-paxos also in the TLA plus proof system. I mean, yeah, we were aware of that work. I can't say that there were necessarily patterns that we like so directly applied or necessarily made this work easier. I think, yeah, I mean, I don't know. I think ultimately, like, a lot of the hardest work was not so much about proof automation, at least with this tooling. It was just more so about reasoning about the protocol, which was just hard, and finding the inductive invariant, I guess. Yeah.
Mm-hmm.
Thank you.
Yep, thanks. Let's thank the speaker again.